So we're going to be talking about gas laws, several gas laws over the course of this chapter. And the first one we're going to focus on is the combined gas law. Okay, so basically the combined gas law gives us the relationships for ideal gases. This is going to allow us to look at the relationships between pressure, volume, and temperature. Let's talk about units first. So as far as pressure goes, right, pressure can be in either atmospheres, millimeters of mercury, torr. Honestly, it can be in any unit you want it to be in. Volume is typically in terms of milliliters or liters. And then here you notice that I have made a big deal out of this. The temperature absolutely must be in terms of Kelvin. For this particular gas law, the combined gas law, the moles are going to be held constant. So we're actually not even going to talk about moles for this particular gas law. Now to help you remember the gas law, so right down here, this is the combined gas law. And so what's happening in this particular gas law is we are changing variables. We may have two different pressures, two different volumes, two different temperatures. And so this is how they will be related to each other. The P1 V1 divided by T1 is equal to P2 V2 divided by T2. Now, what we found is that the easiest way for students to remember this is to draw an inverted triangle where I have pressure, volume, and temperature, right? So PV over T. And then you just label it 1 and 2, right? For my first set of conditions and for my second set of conditions. And you notice up here, and we'll talk about what this means in a little bit, but you notice up here that I have a B, a C, and a G. And that is going to stand for, can these guys possibly be victorious? We'll talk about in the next video exactly how to go about dealing with those particular letters. But for now, we're going to look at this inverted triangle and use this to help us remember the combined gas law is P1 V1 over T1 is equal to P2 V2 over T2. All right, so we are going to do an example involving the combined gas law. All right, so let's go ahead and read through this problem. I'm going to point out how I know it's a a combined gas law, and then I'll show you how to go about rearranging the equation to solve for the variable you want, and then some other important pieces that you're going to want to pay attention to. Okay, so this says a sample of a gas at a pressure of 740 millimeters of mercury has a volume of 2.58 liters and was heated from 24 degrees Celsius to 75 degrees Celsius. The volume of the gas was expanded to 2.81 liters. What is the final pressure of the gas? So you notice in this problem, we have been given an initial pressure, we've been given an initial volume, and we have been given an initial temperature. And then we're telling you we're going to actively change the temperature, which changes the volume, and now I want to know what the new pressure is. So when I'm changing variables, I am dealing with, in this particular case, I'm dealing with the combined gas law because I've been given all of the variables, right? I've been given temperature, volume, and pressure. And so because I have changing conditions and I have all three of those, I know I'm dealing with the combined gas law. So I'm going to go ahead and write out, excuse me, go ahead and write out our equation for the combined gas law. And so it is P1 V1 over T1 is equal to P2 V2 over T2. Okay, one thing I really highly recommend that you do is you go ahead and assign your variables, right? So I have an initial pressure. So that's P1. So P1 is 740 millimeters of mercury. I've been given an initial volume, so V1 is equal to 2.58 liters. And I have been given an initial temperature, right? T1 is 24 degrees Celsius. Now, before I do anything else, I want to go ahead and convert this to Kelvin. And so that is going to be 297.2 Kelvin. And remember that I am using decimal places here when I'm determining the number of significant figures because I am adding. All right, so now I'm going to look for my second set of variables. I have been given a second temperature, which is 75 degrees. And again, I'm going to go ahead and immediately convert that to Kelvin, and that is 348.2. I have a second volume, and that's 2.81 liters. And then here I'm specifically asking for pressure, so that is what I am solving for. Okay, so that's the first thing I go through and do. The next thing I want to do is I want to isolate my equation to solve for P2, right? So this right here is what I'm looking for. So just a quick refresher. I want to isolate P2 and get that by itself. So I'm going to multiply both sides of my equation. If I can write this out, let's see if maybe I can write it over here. So it's T2, B2. There we go. And I'm doing this to isolate P2. So I know then that P2 is equal to P1 V1 T2 over T1 V2. Okay, so now it's a matter of taking my variables and plugging them in. So I am going to take 740 millimeters of mercury times, I may have to erase some of this and rewrite it over here. So let's go ahead and do that. Okay, so I have V2 is 2.81 liters and P2 is what I am looking for. All right, so I'm plugging my variables in. So V1 is 2.58 liters. T2 is 348.2 Kelvin, all divided by T1, which is 297.2 Kelvin, and V2, which is 2.81 liters. Plugging everything in and accounting for significant figures, my final answer is 796 millimeters of mercury. I know that my final unit is in terms of millimeters of mercury. I'm looking for pressure, but if I wasn't sure, my Kelvin units cancel and my liters cancel. And then looking at my significant figures, 740 has 3 significant figures, 2.58 has 3 significant figures, and so does 2.81. Because those variables have the fewest sig figs, my final answer can only have 3 significant figures.